Good morning. We all excited to be here today at DDD? Yeah? Got one person, or was it two? Well, hopefully there's a few more excited at the end of my talk. I'm excited to be here today to talk about computers and aircraft. Just have to wait for some visuals. Okay, aircraft safety is made up of two main things: humans and aircraft. The human part is made up of highly trained pilots and engineers, and the aircraft part is a highly sophisticated machine. So what is this aircraft? It's a machine costing $250 million, weighing 120,000 kilos, carrying 100,000 kilos of fuel and 300 passengers, flying at 1,000 kilometres per hour, powered by 1 million horsepower engines, flying at 40,000 feet above the Earth's surface. Pretty awesome physics going on there. So can I have a show of hands? Who's flown on an aeroplane before? Yeah, it's pretty funny these days. It's just about everyone in the room. Maybe not so funny. Who's got a fear of flying or had some sort of anxiety ever about getting on an aeroplane or being? Okay, you're not alone. I did too. I did my first flight when I was about 18, 19 years old. I remember barreling down the runway and it was all pretty exciting, all the speed. And then as soon as we took off and those wheels left the runway and we left Earth behind and I looked out that window, just as I did, we went through a little bit of cloud base. You get that little bit of buffeting. I looked at the engine and saw it shaking around, the wing flexing. This whole heap of anxiety came through me and I felt very uncomfortable for the rest of the flight. I was like this guy. I had the death grip on the seat. Studies have shown that 40% of the population have a fear of flying or some sort of anxiety. I got over mine because I work in aviation and I know how safe aircraft are now. So hopefully by the end of my talk, anyone that put their hand up about the fear of flying, that will have eased or you'll be free from it by the end of the talk. Three to 4 months ago, I went to Perth Airport. That's where I work. And when I walked into the terminal, it was absolute chaos. There was long lines of people wearing long faces. The check-in system was down. The baggage system was down. Many flights had been cancelled or delayed. And when I got into my workplace, every single computer in my office looked like this. CrowdStrike had struck. So what did that mean for the thousands and thousands of aircraft, all controlled by computers that were in the air at that moment? This is a screenshot of the Plane Finder app, a live view 24/7 of every single aircraft that's in the air. On the left here, we have North America, and on the right, Western Europe, one of the busiest airways in the world, both domestically and internationally between those two regions. Well, absolutely nothing happened to these aircraft. They all flew on very successfully and smoothly to their destinations. Let's have a look at how that's so. First though, before we get into the digital age of aircraft, we have to look at what was before digital. These were mechanical systems on aircraft, commonly referred to as the analog era. You can see here a flight control system. This was a steel cable around a pulley, nuts, bolts, washers, and metallic support structure. It is quite durable, reliable. Occasionally things go wrong, like a stray screw gets jammed between the cable and the pulley, like in this case. You can see the cable's damaged. That's where I come in as the engineer. I have to replace that cable, retension it, re-rig the whole flight control system, have it tested, independently inspected, then I certify it, and then the plane flies again. This costs money with ground time. This is what's now replaced that. This is a full fly-by-wire digital flight control system. So instead of having that metal cable, we now have a copper wire sending the messages from the flight deck to the flight controls. What is the overriding advantage of all this? It's weight. This system is far, far lighter than the analog systems that we just saw before. We now have a further improvement on technology to the copper cable or wire, and that's fibre optic. The fibre optic wiring is now 90% lighter than the copper wire. So you can imagine how much weight this now saves on aircraft. So what is the advantage? What do we do with all this weight that we've pulled out of the aircraft? If collectively, say, we've saved 5,000 kilos of weight, that means you can now put 5,000 kilos more fuel on the aircraft to fly the same aircraft further, increasing efficiencies for airlines and expanding their networks. Or we can take the same aircraft and the airline can uplift 5,000 more kilos of freight or passengers, which means more revenue and more profit, which airlines love. But there's a conundrum with all this technology. When it gets developed and the aircraft manufacturers want to do it or use it, it's unproven. Therefore, it's very dangerous for it to be put in an aircraft application straight away. So when they do see an application for it, they build a test bed and they test it and test it and test it. And then once it's proven to be reliable and it can actually do what they want it to do and do that safely, it then gets approved by the regulators to be put into the building of these aircraft. Today we're going to look at 4 areas of digital tech used on aircraft that are flying today. We have an 8086 Intel microprocessor, a FADEC or full authority digital engine control, a primary flight control computer, and a TCAS computer, a traffic collision avoidance system. The 8086 Intel processor. Has anyone seen one of these before? Worked with them? Knows about them? Good. Does anyone know when this was first developed? When they produced the first one? Correct. You're up the front. You can see the date stamped on it. Full marks to you. 1978. That's a damn long time ago in digital world. These still are used on modern aircraft today. Why? Because they're ultra reliable and durable. No, they're not used in a critical flight control system, but they're used in things like controlling the flushing of a toilet or water coming out of a tap, which are critical to customer comfort. If you're flying along and all the toilets stop on your aeroplane, or you run out of water, you're not flying on to your destination. That aircraft is diverting to the nearest airport to get these systems fixed. This is the Boeing 767-300, an aircraft that came out in the early 80s. Boeing's a very conservative company. It saw the digital era coming, but to be frank, looked almost scared about putting this technology into their aircraft. Airbus was a different story. We'll talk about them in a minute. This was a full analog aircraft. However, they decided to experiment with some glass cockpit instrumentation. Half of it was still analog, half of it was glass or digital. They were so concerned about the heating problems with this tech, like semiconductors, circuit boards overheating. The equipment cooling system was so convoluted, it was the most complicated thing I'd ever seen in my life on an aircraft. They over-engineered it. They were so concerned that it could have been a complete failure altogether, the tech. They designed it so all the glass cockpit could have been removed in the future, and they reinstate a full analog suite of instrumentation in this aircraft. This was 1984. Okay, now we'll come to Airbus. Airbus were trailing Boeing in aircraft sales at this point and wanted to catch up. So this is the A320, released in 1988. This is the world's first full fly-by-wire digital aircraft. So to a lot of fanfare, Air France bought 3 of these. This is one of the first 3. Been flying around for a few months. So Air France and Airbus thought it'd be a good idea to do a flyby and air show in France to promote the aircraft. This is how that flyby ended. The aircraft failed to get altitude at the end of the flyby and crashed into the forest at the perimeter of the airfield. So how do we stop this from happening? This is the primary flight control computer. If we just had one of these and the computer died or became corrupted, we would no longer be able to control our aircraft with obvious consequences. So we have 3. This is what we call triple redundancy. 3 identical computers all talking to each other and cross-checking their health constantly, thousands of times per second, whilst the aircraft is in flight. If one computer does become corrupted or dies, it's like a voting system. The other 2 computers talk to each other and, yes, I agree, that computer on the left is corrupt. So they automatically lock it out of the system. And then the other 2 computers on the right continue to cross-talk and cross-check each other for health, and the aeroplane flies on to its destination. This is the FADEC computer, the full authority digital engine control. That computer's controlling 1 million horsepower coming out the back of this engine. So when the flight crew advance their throttles in the flight deck, it sends a digital message to the FADEC computer. It analyses that input, gives an output to the fuel and air components on the engine, and then the engine produces the power that's been commanded from the flight deck. Everything that happens on this engine is controlled by that computer. Everything. This is the fan case of the computer. It actually lives on the computer. A very reliable and durable computer. I've worked in aviation for 34 years, and I've never seen one of these fail. An average gas turbine engine is on the wing for 8 to 12 years before it needs an overhaul. And that computer lives on that engine for 8 to 12 years. Gets removed for overhaul. The computer goes to a special workshop. They give it an intensive health check, maybe a minor software update if it needs it. Then it gets reinstalled on the overhauled engine, back on the wing for another 8 to 12 years. Very, very impressive technology. And finally, we've got a TCAS computer. This is Traffic Collision Avoidance System. This was mandated by the regulators in the 90s to stop commercial aircraft colliding in air. So how does it work? This computer uses data from other aircraft's transponders that are around it, such as airspeed, angle of attack, heading, to work out if there is another aircraft on a collision course with it. In this case, there is. You can see the aircraft on the left. The TCAS computer has given that flight crew a command of climb, and on the right, a command of descend. That is what it sounds like. So instead of this, we have this. Light aircraft, such as the majority of aircraft you would see at Jandakot Airport, general aviation, are not mandated to have a TCAS computer. In this case, the aircraft on the left does. We still have protection because the TCAS computer on the aircraft on the left has seen the light aircraft, has then issued with the demand of traffic, climb. So instead of this, the aircraft goes up and over, avoiding a collision. This has revolutionised safety, potentially have saved thousands and thousands of lives. Only a few weeks ago, over east, there was a light aircraft crash. No one walked away. One of those pilots had 30 plus years as an airline pilot. So still someone with that amount of experience is susceptible to mid-air collision. This TCAS computer was an absolute game changer in terms of safety. So to summarise today, we've gone through 4 computers or tech that can now make flying a lot safer and more efficient. From controlling a tap, flushing a toilet, avoiding aircraft running into each other, controlling 1 million horsepower from an engine, and controlling all the flight controls on an aircraft. I have one final thought for you. On your way home today, if you're riding a bicycle, on an e-scooter, in your own car, on a bus or a train, even just crossing the road, flying is 48 times safer than all of those modes of transport. Yeah, not 4 or 8, 48 times safer than crossing the road. Flying today has never been safer, except for if you're this cat. This is at Perth Airport, and this cat managed to escape the safety of the baggage hold and made its way to the warmth of the engine on a cold winter's night at Perth Airport. Thank you for your time. I hope you've enjoyed my talk. If you'd like to stay connected, I'm on LinkedIn. You can scan the QR code. How are we for time, Min? Do you have any time for a question?
Around 3 minutes.
Okay.
Questions? Anyone? First question?
So the question is, did the cat die? If you didn't hear, no, it didn't. A very brave baggage handler dived into the back of the engine where it had scurried to when we tried to grab it, and yeah, he grabbed hold of it, but only by the body, and it scratched the hell out of his arms. But the cat did get returned to its owner. How it ended up with that situation was they put the cat in a dog carrier, not a cat carrier or something that was not designed for aircraft, and the cat managed to escape in flight. When the baggage handlers opened the door, it just went pow and yeah, ended up in the, the engine. Next question? Yes? Yes, so it is mandatory on aircraft above a certain max takeoff weight, which is basically any commercial airliner. The reason they don't on the light aircraft is because of weight and integrating it into the systems of the aircraft. It would just be too complicated. So, message there, fly on the biggest aircraft you can.
All right, we've got one last question at the back.
Yes?
How do landings work? Like, because then, from my understanding, they need to decide who goes down and whatnot. So I was wondering how that works.
The process of landing the aeroplane, how does that work?
And how that is also protected from like computers. Like,
Yeah, okay, good question. So those 3 primary flight controls and the flight management computer, which is another computer in the system, all talk to each other. They're using all the navigation aids of equipment and instrumentation on the aircraft. That's ground-based things that they talk to know exactly where they are. GPS is the big one now. They can know exactly where they are in the world at any one time. And yes, they have a checklist, the crew. They put the gear down, they set up their auto brakes, the ground spoilers, and so all they're really doing is actually guiding the aircraft through their instrumentation on to the runway. As soon as those wheels touch down, a whole host of things happen automatically to stop the aeroplane. That's partly why that Air France A320 crashed. Airplanes were not designed to do flybys at air shows. They were designed to take off and land. So the aircraft in a way was confused with the way they set that aircraft up when they did that.
All right.
Okay.
All right, everyone please give a round of applause for Scott.
Thank you.